So this is the UKMT Pink Kangaroo from 2021. The pink is the extension that you take if you're in years 10 and 11 in England. I think in Scotland it's different. If you're in year 9, you take the grey kangaroo extension, which is easier than this. There is a slight rule change for this. It's still 25 questions, but you don't get marks lost for anything wrong. So you may as well guess everything. Before we start this, let me say that this paper was really tough. Like I was shocked at how difficult I found this. You know, I've done lots of senior math challenges, senior extensions, and this was up there. This was a hard paper. I have had a look at the 2021, and it seemed easier just looking through it. So maybe this was just a rogue case, but yeah, don't be surprised if you found this paper tough. There was a few things on it that just that were very harsh. So anyway, let's get into it. So it starts off okay. It's certainly not the warm up that the intermediate challenge has, though, as the first question. Mean age is 21, so the mean is the total over the number of musicians. There are 6 musicians because there are these 3 and then these other 3. And then the total age is going to be 19 plus 20 plus, it's going to be 6 times 21 because that's the mean, which I also know is 19 plus 20 plus 21 plus 3 lots of the same age that's here, so 3n. I can just, of course, work through this, and this is a very much like a GCSE question. But yeah, it's tough for the first one, but anyway, it certainly does get tougher than that. Second question, so I can immediately say that this side and this side are 3, because that's a square, it tells me. So if I just call this side, well, I can say this is 3 and this is 3 as well. If I call this x and this y, then that means that I can call that x and that y, and then that means I got 3 plus x plus 3 plus y plus x plus 3 plus y plus 3 is 30, which I can simplify to make this. But if you look, I'm being asked for the perimeter of the rectangle, and that's x plus y plus x plus y, which is 2x plus 2y, which is what I've got, so that's going to be 18. So it's interesting that I can do that without working out x and y. Question number 3, so subtracting a tenth from x gives the same result as multiplying 10, so I can just set it up, x minus x minus a tenth equals a tenth of x, times everything through by 10, and then maybe just take away x, add 1 to both sides, and you get a ninth when you divide by 9. Excellent. Number 4, so there are probably lots of ways to do this. What I decided was to draw a line coming out of here and then here again. And what I've actually made here is I've made a rhombus that's congruent to, so the same as, all of the rhombuses that are in the picture. Now I can prove that because if this is 360 degrees in the center, that means there are 60 degrees on each of these rhombuses here. So if that's 60, then that's 60, which means this is 120 and 120 because of opposite angles in a rhombus being the same, or any parallelogram, and then of course angles in a quadrilateral being 360. So 60, 60, 120, 120. But if this is 120, so is this and so is this, and that means because it shares the same side as the other rhombuses and has an angle of 120 in here, it's a congruent shape. So this rhombus is the same as the ones in here, and I've just got half of it. So I can just say that's 2.5, and then these are all 5s, and then these are all 2.5s. So I have 6 lots of 5 and 6 lots of 2.5 to add up. And however you do that, you're going to get 45. Quite a nice question, probably lots of other ways to do it. Question number 5, another really nice question, not getting into the horrific stuff just yet. So rectangle on the top left has height of 6, so what I can say is that this width of this rectangle must be 3, because 3 times 6 is 18. If this width is also 3, because it lines up, that means this height is 4. And we keep going in this vein. The height of this 16 is 4, which means its width must be also 4. 4 times 4 is 16, which means this width is 4, which means its height is 8, because 4 times 8 makes 32. If this height is 8, then its width is 6, and if this width is 6, then its height is 5, and we end up finishing. So nice question. Number 6, how many 5-digit positive integers have the product their digits equal to 100? So first, very tough question, I thought, and it's only question 6. So essentially, the best way to do this, I think, is to break 100 into its prime factors. No, sorry, 1,000 into its prime factors. So 1,000 is 10 cubed, clearly. 10 cubed is 2 times 5 cubed, which means it's 2 cubed times 5 cubed, which means it's 2 times 2 times 2 times 5 times 5 times 5. Okay. Now, that's interesting because there are 6 things here multiplying to make 1,000, and I have a number that's only 5 long, and I need to multiply it to make 1,000. So what I'm going to do is I'm going to combine those 2 into a 4, and then say the digits are 4, 2, 5, 5, 5. Those will multiply to 1,000, and it's only 5 digits long. Now, why have I combined these two 2's to a 4? Well, you notice that I can't actually combine the 5's or a 5 and a 2, because if I do, that gives me a 2-digit number. This makes 25, which I can't make a digit, and this makes 10, which I can't make a digit. The only way is to combine the 2's, except I can combine all of the 2's as well to make an 8, and then I could have a digit of 1. because timesing by 1 doesn't change anything. I'll get to that case in a second. For now, though, I have to decide how many numbers there are that look like this, that have these digits. Now, I can change the order, of course, because when I multiply, the order doesn't matter. And the easiest way to think about that, some of you might have done some choosing and rearranging work with, factorials and stuff, but just to assume that you haven't, there's 5 places you could put the 4, here, 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 or here. So you've got 5 choices of where to put the 4, and then wherever you put the 4, you've got 4 choices to put the 2, because you can't put it in the same place, and then you just fill in the 5s into the other places. So there's 5 places to put the 4, 4 places to put the 2, 5 times 4 is 20 rearrangements of this, and then you have that other case I mentioned, where you can combine 3 of the 2's together to make an 8, then just put a 1 in, and then have all the 5s. This will still times to 1,000. And again, same logic for how many choices there are here. It's 5 choices for the 8, 4 choices for the 1, 20 choices in total. Add them up to get 40 choices in total. Tough question for a question 6 of this challenge. They were really testing on this paper. A nicer question here, just GCSE angle stuff, which is nice. This is a right angle, right angle, right angle, right angle in the corners here. So that's good. And if we just focus in on this shape here that you trace around on the top of these kind of lines here, you end up with a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-sided shape. 10 to the 2 is 8 times 180 is 1,440. So that's the total number of degrees in this shape. Take away the 4 lots of 90, which is just 360. You could have saved yourself some work if you had done that earlier, I guess. And you get 1,080 must be the sum of all these angles, because that's what's left in the shape. You could have done that backwards, I guess, and used the smaller shape on the inside, but whatever. Half time in a handball match, the home team was losing 9 to 14. Second half, they scored twice as many. So let's call the number of goals. The visitors scored X. That means that the home team scored 2X in the second half. So at the end of the game, the home team has 9 plus 2X. And the away team has 14, because they started at 14, plus X. So this is the halftime scores. I've added X to the away team and 2X to the home team. And then I've added this 1 because it tells me that the home team won by 1 goal. So I have to add 1 to the losing score to make them balanced. And this is just an equation that I can now solve. If X is 6, I put that into this. I get 9 plus 6 plus another 6, or plus 2 times 6. Is 21, so it must be 21 to 20. Question number 9. I don't know whether there's a good way to do this question. I kind of just guessed, and it worked out well. So apologies if you were looking for true insight into this question here. What I noticed is that there's a 6, which doesn't interfere with this circle up here. And the only other number that doesn't interfere with this circle is this one. So I figured, since 6 is the biggest number and all the circles need to add up to the same thing, and this circle doesn't involve a 6, it probably also can't involve a 1, because that's the smallest number. So if this circle doesn't involve the biggest and the smallest, that seems like the way to make it the most balanced and make it most likely add up to the same thing as the other ones. So I put a 1 here, and then I just played around with a couple of combinations and found that this worked. It didn't take me very long, so X is 1. There's probably a proper way to do that, like considering when you add them all up, and maybe you get, it looks like each one is part of 2 circles, so maybe that's 2 times the total. Maybe you can find the total that a circle has in it by dividing them by 3, because there are 3 circles. I don't know, but that was my logic. Question 10. Okay, so this is the question that shocked me, because I actually know this problem very well, and it seems ridiculously advanced to put as question number 10. It's talking about a staircase game where you can only go up either 1 step or 2 steps every time you go up. Now, I know this problem because I've done work on it before, so I was immediately at a huge advantage when I did this. But I'm struggling to see how you do this so quickly in the middle of a maths challenge as question number 10. Sure, question number 25, make them think about it, but question number 10. Anyway, to get up a 4-step staircase, there are the 5 ways that I've represented here. And the insights that you need here, maybe you don't need it. Maybe you can get away with this question otherwise because it's not really going too high anyway. But the insight that you can take from this question is that the number of ways to get up a 4-step staircase, your last step can either be on the 3, like these cases do, or your previous step could have been on the 2, like these 2 cases do, because then you can jump up 2 stairs. And so the number of ways to get up a 4-step staircase is the number of ways to get up a 3. Essentially, the bottom half of this, this, and this show us the 3 ways to get up a 3-step staircase. Then you add on the extra step. Or you go up a 2-step staircase, like these 2 do, and then you add up the 2 steps. So the number of ways to get up a 4-step staircase is the same as the number of ways to get up a 3, represented by this, this, and this, and this, plus the number of ways to do a 2, which are these 2. And so you actually end up with a Fibonacci sequence, right? So if you plot it out, the number of ways to get up a 1-step staircase is obviously just 1, you just go up 1 stair. To get up a 2, I already showed you, is 2 ways, this, or just jump up straight up. So the number of ways to get up a 2 is 2. Of course, the number of ways to get up a 0 staircase is where the other 1 is from the usual Fibonacci. To get up a 3 is 3, because you add up the previous 2. 4 is 5, as I showed you, and then you keep adding up in a Fibonacci, and you make this sequence here. Now, the problem with this question is there is a hole in the 6th step, so you cannot use that. So that's actually, with the 6th missing, it stays the same until the 5th, obviously. And then when you get to the 6th, so you can't do the 6th, right? Because you can't step on a stair that doesn't exist. But when you consider the 7, that means actually to get up a 7, you can't use the 6th. So the only way to get up a 7 is to use the 5 stairs and then jump up 2. Which means, and that's the only way. So there must also be 8 ways of doing that. You just go up 5 in all the different ways, and then you just go up 2 steps. But also for an 8, because you can't use the 6th, the only way to get up an 8-step staircase is to go to 7, which there are this many ways, and then again, just go up 1 step. So there's only 8 ways to do 8. Ridiculously advanced question, I thought, for that step in the paper. But maybe because the numbers are so small, you could have just trial and errored it rather than know stuff about the problem like I did. A bit like, ironically, I did the 9th question by not even really knowing anything about the question. I just kind of guessed something. Maybe that was what they were going for. Question number 11. There are 5 teams entered the competition. Each team consists of boys, girls. These are the team numbers. Okay, so after one team of girls being knocked out, the number of girls was 3 times the number of boys. Now, what this tells me is there's quite a lot more girls than boys in this competition, because after a team of girls has been knocked out, there are still 3 times the number of girls to boys, which is interesting. Now, essentially what I'm going to do is I'm going to add up all of these numbers to find the total number of competitors, which is this. And now, if this is saying the number of girls competing is 3 times the number of boys, that's a ratio of 3 to 1, which means the number of people still in the competition is a multiple of 4. Because we can't split people in half, and we've got to divide the total by 4 to split this ratio, haven't we? So when I take one of these teams out, after one team of girls gets knocked out, when I take one of these teams out from the total number of competitors, the number remaining must be a multiple of 4, such that I can split it in this ratio nicely. So let's just go through that. Let's do 81 taking away this team. Okay, so that does make a multiple of 4, but when I split it into the 3 to 1 ratio, divide by 3, and then times up, the boys here, this number 18, doesn't represent a team, right? There's no team of 18, and because these teams are completely single-gendered, we can't have a team of 18, so that can't be correct. Okay, so what if I remove a team of 15 from the competition? I get 66. That's not a multiple of 4, so I can't split it without taking decimals. Remove the team of 17. That is a multiple of 4, but when I divide it by 4 and split it into this ratio, again, a team of 16 doesn't exist for the boys to be in, so that's not right. When I remove 19, I get 62, again, not a multiple of 4, so therefore 21 must be the case. We can test it really quickly, but what we see is we get 60 people left, split it into this, and the team of boys must have been the 15 here, and then the 45 is this, and this team. So the answer is 21. Question number 12. 10 sparklers, same size, each sparkler took 2 minutes to burn down completely. Okay, so this question. So, how this is that we need to, it takes 10 sparklers 2 minutes to burn down completely. So, if he just lit the 10, one after the other with no overlap, it would take 10 times 2, 20 minutes to burn down. However, he's going to start with 1/10 of the time left to burn. So 1/10 of 2 minutes is 12 seconds, because 2 minutes is 120 seconds. 1/10 is 12 seconds. And now, just be a bit careful here. I'm going to just remove a bunch of copies of 12 seconds from this time to represent the overlaps. Now, how many overlaps are there? Well, there's 10 sparklers, but there's only 9 overlaps, because you don't pause before doing the first, right? You just light the first, and then there are 9 transitions until the 10th. So 9 times 12 is 108 seconds, so I'm going to remove that from this. If I change it to minutes, it makes it a bit easier. Take away 1 minute 48, and we get 18 minutes 12 seconds left. Cool. Question 13. Beautiful question. From now on, every single class that I teach circle theorems to will get this question at some point. It's already on my resources. I did it in a couple of ways. The first way I did it was much worse. I'll do the cleaner way first. The cleanest way is to notice, well, this is a diameter, so let's use this rule. That makes this angle up here, not including this slither here, just from that line to there is 90, because that is the diameter there. Then notice that this and this are a radius, so this angle here must be 67, which makes, because of the 90 thing, that makes this angle 23, but also this is a radius with this, right? So this here is also an isosceles triangle, which means this must be 32, which makes that must be 9. That's the cleaner way of doing it. The messier way is to say this angle here is 2x based on this rule, because from the same 2 points we're going to the center or we're going to the edge, so that must be 2x. I can call, because of the whole 90 thing again, we need to use this again. I can say that this angle is 23 because it's 180, sorry, it's this triangle has 180 degrees in it, minus 90 minus 67 is 23, which makes this angle here 180 minus 23 minus 2x, just because of this little triangle in here. Which makes this angle the same because it's vertically opposite. And then of course we've got one last triangle which adds up to 180, and it's 157 minus 2x plus 32 plus x is 180, and you can solve for x from there. Much dirtier way, but it gets the job done. Question 14. So if this, let's just say that this box is n, and then we're saying that the total is 2021 plus n. Now, if the total between these two boxes is one more than this, well, it still uses this n box, so this number must be 2022, right? Because it's just one more than this box is. So this total is definitely going to be one more than this total. And we can carry on this same logic. This total needs to be the same as this, but it's already got one more number in it, so this needs to be n minus 1. This total needs to be the same as this, but it's already got one less in it than this has, so this needs to be 2023 to make this add up to the same thing as this does. And continuing the same logic, n minus 2, 2024, and then we just need to add up these two boxes to find t, and we get 4045. Excellent. Question number 15. So just figure out a way to do it first. One goes here, one goes there. We can't use this or this, so that's all blacked out. I think that's one way to make this arrangement work. And then you think, well, how can I change this? Well, I could swap, say, like this one and this one I think would work, because that would still put 2 in this. When I say swap, sorry, what I mean is this goes here, and this goes here. That would still make, there'd be 2 in here, 2 in there, 2 in there, 1 and 1. So that's good. Then I realized I could actually swap it with this could go across, this could go across. And likewise, I could swap this one across, and also this one could go across, which is, I think, is what I did with this one. I swapped this went there, this went there. I could swap all 4 of those to make 5 combinations from the original. And then, okay, so the answer is either D or E. So all I need to do is think really hard, can I find another one? And after about 20 seconds, I was like, no, probably not. I don't think I can. I think it's just going to be 5. There's a bit of logic behind it. I can't use this kind of T section here. I can't put anything in there. I seem to, like, whenever you try and move anything now, you just seem to end up with a copy that you already got. Like, you can only move this box either down to here, which kind of starts giving you this copy, or up to here, which gives you one of these copies. And yeah, it's just kind of logically says 5. Again, in Math Challenge, you're low on time. You probably actually don't want to completely logically prove everything that you do all the time, because that's just going to take way too long. So sometimes just use some intuition and put it down your best thought. Okay, question number 16. There was a race with 5 people in it. First to last is told us that it's Fiona, Gertrude, Hannah, India, and then Janice. And then the finishing order was India, Gertrude, Fiona, Janice, Hannah. So that's the starting order, that's the finishing order. They scored a point every time they overtook. What's the lowest number of points? So all I need to do here is count the fewest number of overtakes. Now, India must have overtaken Hannah, Gertrude, and Fiona, right? Because she was here, and there must have been a point where she got past all 3. So India had to get 3 overtakes. She could have got more, of course, if maybe Janice had overtaken her at the start, and then she overtook Janice, and then everyone else, but we're talking about the lowest number. So we're going to assume that the simplest thing happened. So, okay, India had to get 3. Gertrude didn't overtake anyone, right? Because oh, in fact, no, sorry, that's a lie. She must have overtaken Fiona, because she started in second. She must have overtaken Fiona, because Fiona ended up behind her. So she must have overtaken Fiona. Fiona possibly didn't overtake anyone. She just started first, and then we're saying just got overtaken by Gertrude in India. So Fiona overtook no one. But Janice must have also overtaken Hannah. Hannah just slipped from third place down to fifth. Janice must have overtaken Hannah. And so 5 overtakes is the fewest we can have, hoping that just no one else jostled for position at any point at all. I'm just going to adjust the mic. Okay, so question number 17. So 2021 has remained a 5 when divided by all of these things. So, okay, if I multiply all of these things together and then add 5, this is annoying, but I'm going to do it. That makes this, add 5 is 2029. So that's a number that when divided by any of these, I definitely have a remainder of 5. Now the reason I know that is because it's definitely remainder 0. I mean, if you ignore the 5, it's definitely remainder 0 when you divide by any of these, because they're all factors. Add 5 to get remainder 5. Now this number is too big. So there must be far smaller numbers that do this. And the reason that there are is because when you look at the prime factors of these numbers here that you're multiplying, you end up with loads of unnecessary copies. So 6 is 2 times 3, 7 is 7, 8 is 2 times 2 times 2, 9 is 3 times 3. But like, there are loads of unnecessary numbers here, because if you just condense it down to this, so I've got rid of a 2 from this. Like I've got rid of a 2 from, I've got the 2, the 3, the 7. I've got rid of a 2 from these 3. I've got rid of a 2 there. And I've also got rid of a 3 from these 2. Now the reason I can do that is because if you look at this here, I can still make a 6. There's the 6. I can still make a 7, obviously. I can still make an 8 because I've got this 2, and this 2. And I can still make a 9 from this 3 and this 3. So 6, 7, 8, 9 are all factors of this, because all I've done is get rid of the unnecessary primes that I didn't need. And now I'm sharing the primes, but I've still got enough to get all of these numbers out. Okay, so let's do this then. Let's multiply these, and I get 504. And when I add 5, that gives me 509 definitely has that property, because 6, 7, 8, 9 are all coded into here, and then I add 5 for remainder 5. Now what's the next thing I can do? Well, I can take this, and I can just times by an unnecessary 2. Which gives me 1008. Plus 5 is 1013. And again, all the stuff is still in here, it's fine, because it's still in this bit. And I can do that again, I can times by an unnecessary 3, times that by 3 to make 1512 plus 5, and I get 1517. So that's good. So that's 3 numbers that do it below 2021. If I times by another 2, then I'll just make 2021. If I times by 5, then I'll make something too big, and likewise. So those are the 3 numbers, except you have to be clever enough to notice that 5 also does it, just a plain old 5, because 0 is sort of technically divisible by all of these things. So then when you add 5, you just get remainder 5 by all of these things. So there are actually 1, 2, 3, 4 numbers that do it. It's just a tough question. I mean, it's a tough paper, isn't it? We've already said that. Question 17 is also, gosh, thinking about it, this paper was so hard. Anyway, what I can gather, so students either filled in this section, this section, this section, or this section, but because they're filling in 2 by 2 squares. But the thing about that is that every 2 by 2 square involves the middle number, like this one does, this one does, this one does, this one does. So this middle number represents how many students got up to do a 1, 1, 1, 1 square, right? Because it always goes up no matter which square the students choose. So 47 students did this. Now the next thing I said was that, okay, if 47 students did this and they each marked down 4 numbers, then that means that 4 times 47, 188 is the total of all of these numbers. Okay? Now, the key for the next bit is to notice that if this number says 13, that means that this box was marked 13 times, because none of the other 2 by 2 boxes affect this thing in the corner. So if that's marked 13 times, these boxes were all marked, this square was marked 13 times. I've also said if 188 is total, 110 is what's left between these two things. Okay, what I'm getting at here is that if this is A, if we call this number A, that means this box was marked A times. I know this box was marked 13 times, which means this number here is A plus 13. I don't know why it's not coming up in any good place. Oh, okay, so what I'm saying now is if that's A, B, C, then this 2x2 was marked A times, this was marked C times, this was marked B times, this was marked 13 times. That means that these 4 sum to 47. Take away the 13 makes these 3 sum to 34. Right? As I've said, 47 is affected whether you mark this box, this box, this box, or this box. So this plus this plus this plus this must be 47. Then I'll say, okay, if this box was marked A times and this 13 times, this, because there's no other way to touch it, must have been A plus 13. And likewise, this, in the same logic, must have been C plus B, and this must have been 13 plus B. And so now I have one equation for ABC here, and I'll make another one for adding up all of these red numbers. Sorry, not all the red numbers, adding up all the grey numbers must be that 110 that I had before. So A plus 13, 13 plus B is there, C plus B is here, and then C is there. And also B, sorry, not just the greys, also B, because that's not a number I've been given yet. So also B, add up to make the 127. If you add up that, it very nicely and helpfully turns into this. And of course, if I times that by 2, I end up with this, and the only difference here is a B. So therefore, B must be the difference here, which is 16. Just a horrific question, but it gets worse. Yeah, that's not even the worst thing here. This is quite possibly the worst thing here, but I don't think it is, because I have a question in mind that is even worse than this. Okay, so they play this game, they write down 10 words each. They score 3 points if neither of the other boys had the same word in their list. Score 1 point if one of the other boys had it, and none if all 3 boys have it. Let's consider the only ways that Sam can make 19 points. Either he scores 1 ones, so 1 word one other kid has, and 6 words none of them have. 6 times 3 is 18 plus the 1. Or he writes down 4 words. Now he can't write down 2 words that the other kids have, because if he does that he gets 2 points, which leaves 17, and then he can't get 17 out of a bunch of 3s. And that's the only other way to score points. So the next way is to write 4 ones and 5 of his own. And then after that it's 7 ones and 4 of his own, except this actually can't happen because this is 11 words. 7 ones and 4 threes is 11 words. So that can't happen. So it's one of these 2 cases. And now what we do is we consider each one very carefully. Let's consider if it's this case. If it's this case, 3 words, because there are 1 word here that was shared and 6 words that were unique, there are 3 words that were written by all the boys. So now let's consider James. 3 of his words were written down by all the boys. So the only way for him to beat Sam's score, and remember Sam has the smallest score, the only way for him to beat Sam's score is to therefore all 7 of his words must have been unique. Because 3 of them were definitely written by all the boys, because he scored none for those, Sam did. So James must have scored 7 threes. Now if James scored 7 threes, that means that the other boy, who is unnamed, must have been sharing this one. So he must have got 1 point for this. However, he must have also scored higher than Sam, and they all had different scores. But the only way, if the unnamed boy only had 7 scoring words, which we know, and he had 1 draw, he can only have got 6 threes left in order to try and beat Sam, but he hasn't beaten Sam, he's drawn with Sam, which we know can't happen. So this entire timeline doesn't work. So okay, now we have to consider this timeline, which is the only one that can work. Now this means that 1 word was written by all of them, because 9 words had a point scoring. So 1 word was written by all. So again, let's consider James. Let's say if James got 2 of these pairs with Sam. If James paired 2 of those, that means 2 of his words were paired, 1 was shared by everyone, which means he got 7 3-pointers. Okay, and now let's consider the unnamed boy. He must have also been sharing 2 words. 1 word was written by all, which means he must have also got the same as James. Except, again, ties can't work here, so this doesn't work at all. So that means that James must have got, So this is one thing that could happen. Also, James and the unnamed boy could also share points. They could share a word and still score higher than Sam, but they would still tie in score, so that still can't happen. Okay, so next timeline, one word written by all, but this time James only got one of the pairs with Sam, which means the unnamed boy must have got 3 of them, and that's the only timeline that can work. So James got one of these pairs, the unnamed boy had 3 of them, James got 8 threes left over, which means he definitely scores higher than Sam and the other boy. The other boy scores higher than this because he gets 3 pairs and 6 singles, and then it all works out nicely. And so how many points does James score? 1 times 1 plus 8 times 3 is 25 points. Very difficult logic question, that one. Okay, some nice better maths here, I think. Let n be the smallest number such that the sum of its is this. Okay, so smallest numbers are shortest numbers. That's a saying that I live my life by, it would be fair to say. For example, 99 is smaller than 5,553, despite the fact that they have the same digit sum, because 99 has fewer digits. Right? Bit of year 3 place value there on display. Essentially what that means is, for n to be the smallest positive integer with the sum of its digits 2021, I just want as many of its digits to be 9 as possible, to make the length of the number as small as possible. So let's do 2021 divided by 9. And when I do that, I'm going to find essentially here that I can't just make the number all 9s, because this doesn't go into 9. I need to make the number 224 9s, and then have 5 left over, which is funny because I already knew that based on question number like 14 when we were looking at remainders left over when we divided this by 9, remainder 5, there was a question like that. Anyway, the remainder is 5, so this number, the smallest number that has the digit sum of this, is 224 9s with a random 5 put in the middle of it, except it's not a random 5 because for it to be smallest, the 5 can lead the numbers, because of course, place value again. Smallest number at the front means smallest number. So, okay, so I've got 5 with 224 9s after it. And now what I'm going to do is I'm going to add 2021 to that. And I'm going to do a nice little column. That makes 0 with 1 left over. That makes 11 with 1 left over makes 2, which with still a 1 left over, to make a 0 with 1 left over, to make a 11, 12 with 1 left over. 1 left over here makes 9 to make 10. 1 left over, 9 with a 1 makes 0, 1 left over, and you're just going to end up with a ton of zeros. All the way until you get to 9 plus 1 remainder makes 10, 1 remainder, 5 plus 1 remainder is 6. So it ends up being this, and now for a second I worried about counting exactly how many 9s are in here, but you don't need to count how many zeros are in here, because I'm looking for the digit sum of this number, and zeros obviously don't participate in that. So the digit sum is just 6 plus 2 plus 2 to make 10. Question number 21, another horrific question. Got a square, so I've got some dashes here to represent that these sides are all the same. The square in the picture has area 16, the smallest square. Now this here is the smallest square, because this is the hypotenuse of this triangle, so this length is clearly bigger than this length. So the smallest square has area 16, which means that this side is 4 and this side is 4. That square has side length 4. Now if I call this length x, this is also a square. As indicated by the dashes that I apparently already put here. Which means if I consider this triangle that this x is in, this length here, and this triangle, which has the same hypotenuse, and I'm going straight down, so this is a right angle, they both have right angles. If I call this angle here y, this must be 90 minus y, because this angle is 90. Now this angle here is also 90, which makes if this is 90 minus y and this whole angle is 90, that must be y, this angle in here. Which makes this 90 minus y up here, which means I actually have 2 congruent triangles. They're definitely similar because they all have the same angles, 90y and 90 minus y. So they're definitely similar, same angles, but they also share this side, so they're congruent. So this side must be x. And now the area of this grey triangle is simply a half times base times perpendicular height. So 1 is equal to a half times x, so x is root 2. Good, so x is root 2, that's interesting enough. How do I make more progress here? Well, what I can say is that if this distance here is 4, and this distance here is root 2, then I can use a bit of Pythagoras to work out this distance, which is the side of the largest square. So I'll say the root of root 2 squared, which is this, plus 4 squared, is this side. that of course goes out to 2, 16, root 18. If this side is root 18, then that means this side is root 18, and the area is root 18 times root 18 for 18. Really tough question. Question number 22, another tough one. I use some trig identities, and well, not trig identities, I use some angle identities that I know. If I pop a side straight down here, essentially we're looking for the ratio of this distance to the stairs distance. So I'm going to pop a line down there. I'm going to say that this triangle here, let's just pretend that this length here is 1. Making up numbers is super important math challenge, really does help sometimes. Let's pretend this distance is 1, and now let's look at this right-angled triangle. It means that sine of 60 is equal to 1 over this length, just from basic SOHCAHTOA. Sine of 60 is root 3 over 2, so if I then swap this with this, I get this, root 3 over 2, 1 over a fraction, you just bring the 2 up, so we get the hypotenuse as 2 over root 3. So that's good, that's my first bit done. And now what about this bit? Well, this is kind of interesting. If this is a right angle, which I've already said that it is, then this is a triangle with 60 here, right angle here, which means this angle is 30. And if the entire thing was 75, I can call this 45. And then I notice if this is 45 and this is a right angle, that makes this an isosceles triangle. Which means if this length I've said is 1, so is this length. And now this is really cool. There's lots of complicated ways you could find the length of these stairs. But the easiest way is to notice, if you just look at the horizontal bits, they must add up to 1, because they travel horizontally the same distance as this one does. So the horizontal bits are 1, but also the vertical bits are all 1, because they travel down the same amount this one does. So this distance here is 2. The vertical bits are all 1, the horizontal bits are all added up at 1, so when you travel down this staircase, you're going a distance of 2. If you're sliding down exactly how it goes along. So now we have a ratio of 2 over root 3 to 2. That's our ratio. We can divide by 2, and then we can multiply everything by root 3. And I've done the ratio AB to BC. Let's just check what it wanted. It wanted BC to AB. So swap those two over, and we get the answer of E. Excellent. Only, 3 questions to go? Cool. This question, I think, is the worst thing here. It really tests your logic. Maybe there's an easier way of doing it, but yeah, I just thought this question was really tough. I'm just going to plug my computer in. Just give me a second. Apologies for that. So we've got 200,021 balls arranged in a row. So let's just write out. Now I'm given information about the 20th. So I'm going to be extra enough to write down all of the things down to 20 and then say that the 20th is green and so is the second. Okay, and now I'm going to try and slot in some stuff here. Among any 5 consecutive balls, there is exactly 1 red, 1 yellow, and 1 blue. Let's look at the first 5 balls. Okay, currently they've just got a green in, so that we need a blue, yellow, and red here, except it says after any red, the next is yellow. So a red can't be here, because there's a green after it. So a red is either here, which would make a yellow after it there, or a red is here, which would make a yellow after it there. A red can't be here, because then I've not got any yellows in the first 5. So we've either got this or this. Let's continue with this. If we look at the 5 going from maybe the 3rd to the 8th, if we look, to the 7th, if we look at those 5 balls, 3, 4, 5, 6, 7, we can't have another red here. Because we've already got a red, and we're only allowed exactly 1 red in any 5 balls. So we can't have a red in any of this. But if we look at the next 5 from 4 to 8, I've already said none of those can be red, but we must have a red within these 5 balls from 4 to 8, which means that must be a red. And if that's a red, that must be a yellow. And likewise, exactly below that, use the same logic to work out the one shifted further must be red, which means the one after that must be yellow. So I've got 2 timelines here. I've either got the reds here, starting 3 and then 8, or the reds here. And actually what you can say then is that every 5 there must be a red. If there's only allowed to be 1 red every 5, if you've locked in the 5 at 3 and then at 8, you can just extend that logic, say that this must be also a red in this top timeline, which would also mean that this needs to be, and you just fill it in exactly like so. Now the problem with the second timeline is that it forces a yellow to be where I already knew a green was. So this second timeline does not work. And so the answer between where the red and the yellows goes in the first 5 must be this, because of this green. And now what we need to do is decide where the blues go. Now, one thing that I could do at this point, which I did, was I said, well, look at this. Notice that the reds appear every 5, because again, only one red can appear every 5 balls. So if you've got one here, you must have 1 5 further along. And the yellows appear every 5 for the same logic. So where is 2021 in, as the 5s go along? Well, unfortunately, 2021 is a number divisible by 5, remainder 1. This is 1 above a multiple of 5. So I know that the numbers 3 above a multiple of 5 are all red, and 4 above a multiple of 5 are all yellow, but I'm looking for the 1 above a multiple of 5. I'm essentially looking for what these colors are and what these colors are. And so I still need to work out whether they're green or blue. So what I did here was, again, I made 2 timelines. I said, what if a green goes first and forces a blue here? Okay, now I've got 1 blue, 1 yellow, 1 red in the first 5, that's good. Now this here isn't allowed to be a red, yellow, or blue, because then it duplicates with these too soon, so that must be a green. Likewise, this must also be a green, for the same reason, because I'm only allowed 1 red, yellow, blue in this section, which means this must be a blue. And same logic, that means the blues turn up every multiple of 5. So I'm going to fill in the blues every multiple of 5, and the greens just need to fill in everywhere else. Except, if the blues are multiples of 5 now, that contradicts this statement where greens is 20. So that can't be the timeline. Go back, start with the blue instead, fill in this to be a green, and then go blue every 1 above multiple of 5. Fill in greens everywhere else, and that does actually work because it doesn't interfere with this green. And so this must be the order. Blues are 1 above a multiple of 5. 2021 is 1 above a multiple of 5, so that must be blue. I think actually the last 2 questions are slightly easier, though having said that, maybe this question is only I found easier because I recognized what to do quite quickly. I think maybe some other people would find this hard too. I cannot stress enough how tough this paper was. Each of the numbers m and m is the square of an integer. So let's write m is a squared, where a is some integer, and n is b squared, where b is some integer. M minus n, therefore, m minus n is a squared minus b squared. And as soon as I see this, I'm happy, because I can do this to it. And I know Maths Challenge wants me to do that to it. Like, I know it does. Okay, now, if m minus n is a prime, currently I've got it written as a product. I've got m minus n written as this times this. So if it's prime, one of these 2 things must be 1. That's the whole point of prime numbers. You can only write them as a product if one of them is 1. 7 is 1 times 7 only. So one of these must be 1. Well, again, if a and b are positive integers, that means that this one must be 1, because it's clearly the smaller one. So that must be 1. Okay, now let's just try some things. Use the answers. If n is 100, that means that b was 10, because 10 squared is 100. But if a minus b must be 1, that makes a 11, because we get 11 minus 10 is 1. And now we just put it into here, m minus n, just put in the a and the b. That's 1, which is good, but this isn't prime. We get 21, which isn't prime. So this doesn't work. So we try the next one. If n is 144, that means b was 12, which based on this statement makes a 13, because we must make 1 to have even a hope of being prime. But again, it doesn't make it prime because the sum isn't prime. It's 25. So we cross that one off, we keep going, and we just do the same thing a couple of times. 33 isn't prime. When we get to 900, we end up with 61, which is prime, and so the answer is 900. You can test this if you want to. You get 100 and 101 as your 2 a and b's. 100 plus 101 is 201, which is not prime because its digit sum is 3, which means it's divisible by 3, so this doesn't work either. But that one does. 25. Really interesting question, very confusing question initially. 8 coins whose weights in grams are different integers. When Christina puts any 2 coins in one pan, her balance scales, and any 2 in the other balance, the side containing the heaviest coins is always the heaviest side. Now, for a moment, I thought that meant that she had some kind of magical Maths Challenge set of scales that just automatically went down for just whichever of the 4 coins was the heaviest, but it doesn't. This is a normal balance scale. So what it means is just that the heaviest coin in any group of 4 is always just much heavier than the other 3. So okay, let's just put down the 8 coins and think about their weights. Let's just pretend coin 1 has weight 1. And now this is good because what is the smallest possible weight of the heaviest? Of course, when you have a list of weights that might actually do this, you could just times them by 2 and make a new list that could do it, or by 3 and make another list. So if we're trying to go for the smallest, let's just start with the smallest integer as the smallest coin. And these coins are in order of weight, I should also say. Or mass, I should probably really say. Okay, so coin 1 has mass 1. Coin 2 can have mass 2, that's fine, and coin 3 can have mass 3. Now coin 4, when you weigh these 4 coins, coin 4 must always make the balance scales go down on its side. So if coin 4 just weighed 4, and you put this coin with coin 1, and coin 2 and 3 on the other one, coin 4 and coin 1 would weigh 5, 4 plus 1 is 5, but these would also weigh 5, and then the balance scales would be balanced. So that can't work. So coin 4 must weigh 1 more than that, to make 5 plus 1 just heavier than 2 plus 3. And likewise for coin 5, when you look at the smallest coin it could be weighed with is again 1, and the largest thing it could be weighed against that pairing is 3 and 4. So coin 5 must weigh at least what 3 and 4 do, because then when I add the 1, I'll make these two heavier. And you might recognize this sequence because it's again the Fibonacci sequence, which we saw earlier. Essentially, whatever the next coin has to be, it just has to weigh at least as much as the 2 before it, because that's the heaviest combination that it could go up against, along with 1 that it could go with. That's the least that it could go with. And we end up with coin 8 being a weight of 34. So really interesting that question 25 was just spotting a Fibonacci pattern, but like question 10 was spotting a Fibonacci pattern in, I thought, a more difficult version, but then also asked you to do something else afterwards as well. So props to whatever the UK Math Challenge writers were smoking when they wrote this paper. This was a horrific paper. I've said it a few times. Really well done for, researching and practicing this challenge before you take it. You're onto a good thing there. This paper was disgusting, and it should have been gone over properly. I thought it was too hard. But so well done if you did well.